Welcome back, chemistry students. We are going to start chapter 12, which is on liquids and solids. And in order to talk about liquids and solids, we need to talk about intermolecular forces, or IMFs. The definition of an intermolecular force is an attractive force between molecules. Intramolecular is between the atoms, and we bond them together. We're talking inter, between multiple molecules. IMFs account for multiple things. I already mentioned the fact that even to have a liquid or a solid, you must have IMFs present. We also see them as the interactions that cause surface tension and viscosity. A good example of IMFs in action are physiological processes, such as this man tasting the caffeine in his coffee. This tongue, with all of its various zones for sweet, salty taste, sour taste, bitter taste in the back. If you zoom in on it at the molecular scale, you'd see something like a protein that could sit up here and be a receptor for caffeine to enter and would give coffee its characteristic bitter taste. This is an example of an intermolecular force acting between receptors of the taste bud and the caffeine molecule. Let's first of all talk about how IMFs account for liquids and solid states. Now, we have rehearsed the kinetic molecular theory and how it accounts for the motions of molecules in the gas phase, the liquid phase, and solid phase. And let's go through that one more time. We say in the gas phase, the molecules or the atoms are totally independent and fast-moving, and they have no IMFs operating. But in the liquid phase, which is more dense, the molecules are close together and can set up IMFs. They make and break these IMFs. They're in motion. But in the solid form, the molecules have become very slow. This is at a lower temperature, and they're basically only vibrating. And the IMFs can be strong in this phase. Because liquids have this make and break mode of setting up IMF, they fit the form of any container. But solids are rigid and do not have this same property.
This is an interesting time-lapse video. The structure of ice shown here. It's the pretty hexagon structure. And as it's heated, the intermolecular forces between the water molecules break apart and it collapses into the liquid phase, which you've seen here. And water has this interesting property, it's very unique, that as a solid it's less dense than as a liquid.
Tomorrow you're going to perform a lab activity, and the output of this is a heating curve for ice transitioning to steam. It doesn't sound very interesting, but it's actually a really important exercise, and the results might surprise you. So we're going to use the vernier temperature probe and your calculator, and we're just going to make the ice super cold, get it below zero if we at all can, and then we're going to slowly warm it up and take this plot from below 0 degrees to above 100 degrees, and we're going to save that graph and use it quite a bit in this unit. It will be very informative to us. You can tell if a material has strong IMFs because it will have higher surface tension or higher viscosity. It's directly related to these aspects. So when we talk about surface tension, we're talking about how the molecules at the surface form a skin of sorts, and it has to do with their interactions can just be side by side and down. They don't have any neighbors above them, and so you have this, in effect, an outer skin that holds it all together. And a really good example of this is how water forms spherical droplets. The spherical water drops are an outcome of high surface tension. Water has a very high surface tension because water has the ability to hydrogen bond, which is one of the IMF types. And I have an interesting little video clip here of astronauts drinking water in space. These spherical water droplets float. There's one other property that's characteristic of strong IMFs, and that's viscosity. When we have a viscous material such as maple syrup, it's because the IMFs are strong between the molecules. We see oils, they have long hydrocarbon chains, and they're more viscous than gasoline, which has short hydrocarbon chains. Long hydrocarbon chains have more of a chance to set up interactions with each other, and it makes them sluggish and resistant to flow. And that's how we define viscosity. So in summary, intermolecular forces account for the very fact that we have liquid and solid phases, physiological interactions such as that of taste, and surface tension and viscosity. As we move through this chapter, you'll become more skilled in predicting types of properties that a material will have based on the IMFs the molecule is capable of. Thanks for your attention.